Okay, so good evening. May I request, actually, many of you are sitting quite into a cluster at the back. Is it possible for you two people to just come in the front, especially those at the back? It's not looking like just a cluster of people sitting at one corner of auditorium. So please, if you can come down here, it will be nice. Okay. So with that, let us start today's colloquium. Okay, today we are having this colloquium on which is titled as Bose, a Forgotten Hero. Apparently, Bose went to Presidency and Calcutta University and studied between 1909 and 1913. Almost exactly after 70 years, two very young chaps walked into Presidency College, and one of them is today's speaker. The other one is the one who is going to introduce today's speaker. Okay, so the first one, of course, is Sreerup, who also not only studied in Presidency but also went on doing Calcutta University. And the introductor, if I can call that word, is Gautam Mandal, who is going to introduce Sreerup today. Thank you.
Can everybody hear me? So, first, Arnav has given me this task of saying that this talk is being webcast live on the Facebook page of Chai and Why. So, people who are present in the audience here and they have friends who may have wanted to come but couldn't, you can send them a message saying this. Of course, keep your mobile on silent. So there's so many things to say about Sreerup that I have even written it up so that I don't go overboard. Last time the speaker had to come out of the wings and drag me from stage. So I don't want to do that. So it's indeed a great pleasure for me to introduce my friend and today's speaker, Professor Sreerup Raychaudhuri. As Shotno mentioned, mentioned, we met each other several decades ago, 39 years ago to be precise, on the corridors of Presidency College, Kolkata, as fellow students of the 1980 physics honors batch. After he graduated, Sreerup did his MSc and PhD from Calcutta University and did postdoctoral work, first in TIFR and then at CERN, Geneva. He came back to India in 1999 to join the faculty of IIT Kanpur, where he taught for 8 years. During this period, he has taught probably half the young academic faculty of India today. You toss a coin and you pick an academic faculty, he or she has perhaps been taught by Sreerup. From 2007, he is with us at TIFR as a professor of theoretical physics. Professionally, Sreerup's area of research is in the physics of elementary particles, especially their electroweak interactions. Rather than going technical, let me say that he is one of the very few people in the country whose expertise spans all the way from the mathematics of these interactions to the nitty-gritties of their experimental manifestations in the large underground colliders, such as the one in Geneva. He searches for possible mismatches between theory and experiment, and sometimes looks into extra dimensions and other places for solutions. He has written a rather well-known book by now on the subject of his research. This much perhaps you can find in Google. What is perhaps less widely known outside of TIFR and IIT Kanpur is that Sreerup is a great teacher and he's a great public speaker, an example of which you are going to see here today. What is perhaps even less widely known is the fact that Sreerup is like a walking encyclopedia on an amazingly large number of topics. He says that he has this problem that once he reads something, he finds it hard to forget. I wish we all suffered from this problem. I will end with an anecdote related to this. Once our two families were visiting Paris together. Before the trip, we asked Sreerup to tell us something about the French Revolution. Sreerup did, starting more or less from the inception of the human civilization. Time was short, otherwise he would have started from the Big Bang. The history of human civilization, of course, includes the history of development of science in India and of great Indian scientists, of whom S.N. Bose is perhaps one of the least understood. Without taking, therefore, any further time, let me welcome Sreerup to give the talk.
Okay, so thank you, Gautam, for that hugely exaggerated introduction. And thank you, Satya, and other organizers of the ASET Colloquium for giving this opportunity for me to tell you about Bose, a forgotten hero. So there are many Boses who are heroes in India. This is about one of them. And in case you're worried about what this strange object pictured here is, this is a simulation of a Bose-Einstein condensate, which contains his name, but as you will see is not his primary work. And of course, if you want to see another example of a Bose-Einstein condensate, just look around you at this hall. People are all in one state and the other states are empty. So, okay, so here is the gentleman himself. Okay. So, let me start by taking you back to the year 1895. In the year 1895, people had this idea, which came from a couple of centuries before, of an atom, of atoms, of materials being made of atoms, and atoms were thought to be indivisible. So, from the word atomos in Greek, which means indivisible. And this was the idea. But within 10 years, the idea had changed. People knew that the atom had a structure, had an inner structure. They were not sure that it had something, what the structure was, but they knew there was an inner structure, that there was some dynamics inside the atom. By the time another 10 years had gone by, people knew much more about the structure. They had this classical picture of a central nucleus and electrons going around it. Another 10 years, and this classical picture went away to be replaced by a picture of shifting orbitals of different probabilities, distributions, and so on. So it was a different atom. So from 1895 to 1925, these 30 years have been described by George Gamow as 30 years that shook physics. Now, of course, the people who made this, so I have a panel of the great people who created this physics, all familiar names to you: Max Planck, Einstein, Bohr, Born, Schrödinger, de Broglie, Pauli, Heisenberg, Jordan, Dirac, then Bose here, Fermi, Gamow, Wigner, and Landau, all the people who made major contributions to this revolution. And of course, when you do things like that, Nobel Prizes showered on these people. So all these people who are crowned here, one crowned with the Nobel Prize, they are Nobel laureates, except for just three: Jordan, Gamow, and Bose, who is the topic of our discussion today. And of course, Bose stands out among all of these because, as you can see, all the others are Europeans, and he is definitely not. Okay, so all good stories should begin with once upon a time. So once upon a time, there lived in Germany an optician called Joseph von Fraunhofer. And what he did was he invented the spectroscope. So those of you who have done this experiment with the spectroscope in the laboratory, see, it's not so different from what it is today. So here is, except that you have a stand to hold the prism. Now, with this spectroscope, when people look at the sun, for example, look at the sun and you get a spectrum. Of course, spectrum had been discovered by Newton, but what you find is that inside the spectrum, there are these black lines, which are today called the Fraunhofer lines. Now, nobody had any clue at the time of Fraunhofer where these lines come from. But people did discover soon after that if you look at the sun during a solar eclipse, the same lines, you see, watch this happen, the same lines become bright lines. The dark lines become bright lines. So nobody had an understanding of this. But we know the answer, of course, today, that those are absorption spectra, these are emission spectra. But the answer came only half a century later. How did that come about? There was this gentleman called Robert Bunsen, who invented a familiar instrument called the Bunsen burner. And that generated high enough temperatures in the laboratory to vaporize many of the common reagents and salts. And between Bunsen and his collaborator Kirchhoff, they found that many of the Fraunhofer lines matched with the line spectra of the elements. So then came the possibility that the solar atmosphere contains those elements, and what you are seeing is the absorption spectra. Why? It is also Kirchhoff who proved from thermodynamics that the absorption and emission spectra must be the same. So if I put it in mathematical language, then the emission coefficient and absorption coefficient are proportional to each other for a given wavelength. This proportionality constant, of course, will be the same as if I set A lambda, or the absorption coefficient, to 1, which means it's the emission coefficient of a perfect blackbody. So what we do know is that this has to be a constant for all materials, but it's a function of the wavelength and also a function of temperature. So the challenge was to find this function, which is also known as the blackbody spectrum. So that was the challenge to find it. Okay, so now of course we all know what the blackbody spectrum looks like. So it has this, it's a peaked curve gradually going to 0, and as you increase the temperature, the peak grows higher and moves more towards smaller wavelengths. Okay, this is where the optical range is. And then you have whatever, infrared, ultraviolet, and so on. So the first people to actually do this in detail, worked out the blackbody spectra beyond the optical range, were two gentlemen called Otto Lume and Ernst Springsheim. So Lume-Springsheim experiments were the most precise experiments done in the 19th century on the measurement of the blackbody spectrum. But of course, a curve like this calls out, or cries out for an explanation. So the first person to try giving an explanation was Willy Wien, and what Wien did was he had a formula which was based on some emission probabilities, and that gave a curve which matched nicely at these small wavelengths, but failed badly when you go to large wavelengths. So this is, it should correspond to the 7000 K curve, but as you see, the deviation becomes bigger and bigger as you go to large wavelengths. A similar formula was derived by two Englishmen, Lord Rayleigh and Sir James Jeans, and they had the opposite thing. They had a success for the large wavelengths, small frequencies, but when you went to smaller wavelengths, the curve started deviating, and even worse, it went on and on to diverge or become infinity when you went to very small wavelengths. So that was known at that time, that when you go to small wavelengths, which is the ultraviolet part of the spectrum, you get a catastrophe. I mean, the blackbody spectrum goes to infinity, which of course can't happen because a finite amount of energy is being radiated. Now, the failure of the Rayleigh-Jeans formula gave a big jolt to classical physics at the turn of the 20th century. Now, let me explain why. Because Kirchhoff, in proving his famous law, had shown that the radiation confined inside a cavity has the same spectrum as the radiation emitted by a blackbody. So imagine a cavity with insulating walls, and radiation is being reflected around inside, and this little hole through which one of them comes out, a little bit comes out. Now the spectrum of this radiation will be identical as if it was coming from a perfect blackbody. So this was nicely proved by Kirchhoff using thermodynamics. And then Boltzmann, so Ludwig Boltzmann, using this idea, he had proved that the radiation emitted by a blackbody per unit area is proportional to the temperature to the 4th power, which had already been empirically discovered by Stefan. So this result was already known. So that means that Kirchhoff's idea was quite good. Now, what the Rayleigh-Jeans formula did was it simply counted the number of degrees of freedom of this cavity radiation and then gave each of them the same energy, which is the obvious thing you would like to do. So, what happened? So, Rayleigh did this first part. He counted the number of vibration modes of a standing wave inside a cavity and found that the number between a certain frequency and a little change in that is this. Okay. Of course, multiplied by d nu, I have written that. So, 4 pi nu squared by c cubed, fairly simple. Okay. Now, James-Jeans pointed out that of course, if it is radiation, then it is light, electromagnetic waves, so they are transverse. And if they are transverse, then there are 2 transverse modes of polarization, so you should multiply by a factor of 2. And then there was a law of equipartition of energy proved by Boltzmann, which said that each of these modes gets an equal amount of energy, Boltzmann constant times the temperature. So, plug that in. So, when you multiply all of these, you get this formula. So, the energy goes as the frequency squared times the temperature. So, frequency is inversely proportional to wavelength. So, this goes inversely as the wavelength squared, which means that as the wavelength goes to 0, this goes to infinity. So, this is the Rayleigh-Jeans law, and as you see, this gives you also an ultraviolet catastrophe. Okay, all known stuff. But the question is, what was going on then? Because you can hardly think of something simpler. Count the modes, give the modes energy, and that's it. So, where could one have gone wrong? So, what are the assumptions which went into this? The wave nature of radiation was no longer in doubt. And you still show these simple experiments in the laboratory. The diffraction pattern from a laser. And the counting of standing wave modes is straightforward. You do it in high school. Similarly, there is no doubt that light can be polarized. If you have a polarizer lens, look through it and you see that light can certainly be polarized. There is no question about this. So, go back to Sherlock Holmes. So, what did he say? It is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. So, only one left is the equipartition theorem. But how? It is proved very simply. So, let us take a look at that, closer look at it. The amount of energy which can go into any mode is arbitrary. Let us say it is a quantity E. The probability for this is given by the Boltzmann factor, exponential of minus E by Boltzmann constant into temperature. So, average energy is easy to calculate. Okay? Average energy is the energy multiplied by this number, the probability, divided by the integrated over all energies divided by the total probability. So, replace NE by this formula, Boltzmann factor, any constant will cancel out. So, you have these two simple integrals. Now, go ahead, this is not difficult to do this integral. Do the integrals. The integral here is kT whole squared, it is kT. So, the ratio is kT. So, that was Boltzmann's result, equipartition of energy. So, hard to pick a flaw in this. And this is the classical equipartition theorem. So, in 1900, Max Planck, while playing around with this idea, he made an inspired guess. So, what if the energy values, instead of being continuous and being integrated over, they are integral multiples of some energy packet. Okay? So, the energy, nth energy state is n times some fixed amount of energy. Let us just suppose it is true for the moment. So, same formula as before, okay? Except that now these integrals should be replaced by sums, all right? Sum with the probability of each. So, same probability, I have just put the energy here, multiplied by those, and now you do the sums. Use your basic school algebra to do the sums. So, if you do those, the upper term gives you this factor, it gives you this factor, and as you see, one of these factors cancel, and what you have is this fixed number by E naught by kT minus 1. This comes from the sum. So, this seems to be a new kind of equipartition theorem. It is not kT, but it is this. Of course, if kT is small, we will come to that, then it will reduce to the previous formula. Sorry, if T is large. For small values of E, if E is small, then this reduces as you see. So expand this as 1 plus this. So the 1's cancel, E naught cancels, this goes upstairs and you get Kb. So this is the result used by Lagrange. So what he pointed out is that for small values of E naught, this does reduce to the Rayleigh's formula. But suppose E naught is a little larger, then you should use the full formula. Okay, now where did the Rayleigh's formula work? He concluded that the small values of E must occur where the Rayleigh's law works, and that we saw was for small frequencies. Large wavelengths, small frequencies. So he concluded that when you have small frequencies, you will get small E naught. And that means, at least to a first approximation, you can take E naught proportional to the frequency, which you can write in terms of a constant, and that of course is the famous Planck's law, and that constant we are familiar is Planck's constant. Okay. When you plug these in, so your average energy, you have now plugged in h nu instead of E naught, and hence you get a blackbody spectrum, which is now 4 pi nu square. This is the Rayleigh factor, this is the Jeans factor, and now this is the Planck factor. So if you put them all together, you get what is called the Planck distribution formula. And if you take the approximations of low frequencies, this will match with the Rayleigh-Jeans formula. If you take it at high frequencies, you neglect the other one, for example, you will end up with the Wien's formula. But as you can see here, that of course this will behave like the Rayleigh for low frequencies, but then as you go to, as nu becomes small, then there is a factor which takes it to 0. This factor will take it to 0. So it goes to 0, so that means there is a peak in between. And that is precisely the qualitative feature of the observed blackbody spectrum. But in fact, it also matches the quantitative features of the observed blackbody spectrum. For example, you find the peak simply by differentiating, and you get this formula. So if you can neglect this term, which can be done unless the energies are very high, you get this peak frequency is proportional to temperature, and this is your Wien's constant. Similarly, so this is Wien's displacement law. Similarly, the total energy radiated, instead of differentiating, you integrate the total energy, you will get the T to the 4 law and some constant here, which is the Stefan constant. And since you know the Wien constant and the Stefan constant, you can work out the value of both H and of K. So K you can work out from other things, electrochemistry for example, that matched nicely, and the Planck's constant was derived value from here. The experiment was then carried out by Luhmer and Pringsheim, and they looked at various things. So here are the curves along to Planck's formula, and here are their experimental data. So if you get such good experimental data, then the theory has to be right. Okay. In fact, if you do it in an undergraduate lab, your teacher will suspect you have fudged the data. So, all right. So therefore, we have to accept this idea that energy values, instead of being continuous, there must be integral multiples of this kind of an energy packet, which Planck described as a quantum of energy. Quantum just means a fixed amount. But then you can ask this question, what is the sense of talking of the energy of a wave? It's a wave. Waves can have all possible energies. So how can we think of the energy of a wave being tied into packets? Okay. So that question remains. But Planck thought that he had an explanation. Of course, the question occurred to him as to anybody else, that this is something outrageous which he had assumed. So what he said was that, okay, we have a cavity, let's say there's a little hole through which the radiation escapes, but there are oscillators in the walls and they are emitting the radiation. So they emit radiation, they come out from the, and then when they are in the middle of the cavity, then they merge together to form waves. So you get these continuous standing wave patterns. So therefore, when the emission happens, you get the packets. That's a property of these oscillators in the walls. And when they merge and form waves, then they give you your usual Rayleigh formula, the Rayleigh, that 4 pi nu square over C. So the analogy he gave was that you imagine droplets of water emerging from a tap. Okay, they are discrete droplets. Okay, but if there are enough of them, so But if there are enough of them, there is a continuous stream. So that was his analogy, that the things are emitted discretely, but they become continuous. Nice idea, but alas for Planck, his own best friend, a gentleman called Albert Einstein, he immediately killed the idea. What did he do? He studied the photoelectric effect. And this is something everyone studies. You know that photoelectrons come, and if they remain as packets and are absorbed as packets of energy h nu, then it gives you the kinetic energy plus the work function, and that's the Einstein photoelectric equation, and it shows that energy is also absorbed in packets. Okay. Well, if energy is emitted and absorbed as packets, then it must be packets in between, right? It cannot become merged and then know that it's going to be absorbed by someone and at that point decide to become packets again. This is not possible. So that means it remains as packets throughout. So, of course, this idea was very unpalatable to people at that time. In fact, Millikan, okay, great experimentalist from America, he found this idea so repulsive that he decided that he was going to forever kill it by disproving Einstein's equation. So he set up this beautiful experiment where you create photoelectrons, take out their energy, use a stopping potential to measure the kinetic energy, and proof. So here are his results. So this is the fact, and then he plots frequency versus the voltage, stopping voltage, which is the kinetic energy, and he finds almost a very nice straight line. Once again, if you do this in the undergraduate laboratory, you will be suspected. So instead of disproving Einstein's theory, he proved it completely right. Okay. This is the standard proof you will find in the textbooks, which says Millikans' experiment proved Einstein right. What you don't find in the textbooks is that Millikan started off by trying to prove Einstein wrong. And so Einstein won the Nobel Prize, as you know, for the photoelectric effect. And he had the last laugh. Okay. As a consolation, Millikan also won the Nobel Prize, essentially for this work. Okay. In 1923, Compton found that these energy packets could also scatter off electrons, causing them to recoil, and from that recoil he concluded that they also carry momentum. So now, if they carry both momentum and energy, then they must be particles of light. Something which carries both energy and momentum is behaving like a particle, so it must be a particle. So, you remember this gentleman told us that light is particles, corpuscles. So, we are back to that stage. Is light corpuscles or is it waves? The controversy came back. Big puzzle. Again, people didn't know what's going on. All right. So, over the next several years, there were many attempts to understand Planck's law and to derive it in different ways. So, I will just quickly describe some of those to you. Of course, Planck's derivation I have gone through. So, it was 1900, and that's the young Planck. Okay? It looked a little different from the other pictures. All right. Debye used a probability idea to derive the energy transfer from the cavity to the radiation. So, he was still using Planck's idea that the cavity emits the radiation and so on, but he used some ideas of probability, which we will use later. Then Nathanson, he actually showed that this probability will work if photons are indistinguishable. As we will see, he was a forerunner of the things which Bose used. Okay, in fact, he is another very much forgotten hero. Those who remember Bose, nobody has probably heard of Nathanson. Ehrenfest and Camerlingons, they pointed out that Einstein's photons could not be Planck's distinguishable light quanta. Okay. So, basically putting on the same idea, but not quite getting hold of it. Einstein himself combined Bohr's theory of emission with Planck's oscillators. That is, he invented the A and B coefficients for spontaneous stimulated emission and so on. That's still used to understand high intensity things for lasers. Then came Pauli. So, Pauli tried to understand this, 1923, collisions of Maxwellian electrons. So, electrons have a Maxwell distribution having a nonlinear interaction with the photons. But the interesting thing here was that this is the density of the radiation, rho, before the interaction. This is the density after the interaction. So somehow at the time of point of interaction, the photons have to know what the future density is going to be. So there was a problem with causality in this. Einstein and Ehrenfest got together, and instead of electrons, they used Bohr atoms interacting with discrete energy levels, and they showed that the same thing can happen. The collisions of these Maxwell electrons would, or the width of photons with these Maxwell electrons, or the atoms, would also give you the proper Planck distribution. Now, all of these derivations assume the classical statistics, the Maxwell-Boltzmann distribution, and therefore, none of them were quite right. We still use some of these derivations for high intensity radiation, which is for photons, but that's a different story. The solution, when it came from a quite different part of the world. And on this world map, let me remind you that most of these developments had been taking place in Germany or on the continent of Europe, okay, with Millikans experiments being done in America. But the solution came from this part, which, as you see, to the people there at least, it was a remote part of the world. Okay, so I'll now move on to the next part of my talks to tell you how this solution came, and I'll tell you about the making of ASET Bose. So, okay, so let me take you to a Google map of Calcutta. And this is the river Hooghly, and this is the northern part of Calcutta. Here is the Maidan. And if you go closer to this point, then you see that it's a heavily congested, heavily built up area of North Calcutta. And here there is a road called Ishwar Mill Lane. Okay. The Scottish Church College, well-known Scottish Church College is here. This area is called Goa Bagan, and here is the Ishwar Mill Lane. So in this house, okay, in Ishwar Mill Lane, ASET Bose was born in this house on the 1st of January 1894. Okay, and that's a genuine date. So as you see, Bose's descendants have kept the house in good condition, but yes, but the area is quite a congested area. Now, Bose's father, Satyendra Nath, was an accountant in the East Indian Railways. In those days, for an Indian to be an accountant was actually quite a high position, and he was also a highly cultured man. So he knew a lot of it about various subjects, about science, and you'll see that this showed up in his son also. He also founded a small factory manufacturing chemicals. So he was interested in that. And Bose's mother was called Amodini, and she bore 7 children, which was not unusual in those days. And Satyendra Nath was the only son, and there were 6 daughters after that. Okay, so this is what they really look like in old age. And if you look at Bose's father, you will see some pictures of him. You see, he resembled his father very greatly when it came to the same age. So the young Bose, we have only this little picture of him, was educated till the age of 12 in local schools. He was a bright student, especially strong in mathematics. And there was a reason for this. See, his father would leave him a bunch of mathematical problems to solve before leaving for office. And when he came home in the evening, he would find they were all neatly done. So Bose really loved doing those problems. And this whetted the young boy's appetite for more and more complicated scientific problems. So he wanted tougher problems, more difficult things. Of course, later the mathematics became more complicated, as Gautam is correctly pointing out. Okay. So then when he was 11 years old, the first partition of Bengal was made by Lord Curzon. And this whole area, Bengal, Assam, parts of Bihar, parts of Orissa, all of it together was the Bengal Presidency. And Curzon decided to break it up into 2 parts and essentially on communal lines. So I'll show you this little clip. I hope it works. Yes. This is from Satyajit Ray's film on Tagore, Rabindranath Tagore, and it shows Tagore's contribution. So there was an outpouring of protest from both sides of Bengal. And part of it was embodied in this using the festival of Rakhi, which we have just concluded a few days back, to promote communal harmony. And this is when Tagore composed a very, very famous song, which is still sung, especially on these occasions. Okay, so these stirring events, they left an indelible mark on the soul of the young Satyendra Nath Bose. So there was a very deep-rooted nationalism, deep-rooted patriotism in him, which lasted all his life, and you'll see more examples of that. Of course, in the Delhi Darbar of 1911, this grand Darbar, the partition was annulled when Bose was still a student, 1911. Of course, at the price of the capital city being moved from Calcutta to Delhi. At the age of 12, Satyendra Nath was admitted to the very iconic Hindu school, which was the nursery of the Bengal Renaissance. Okay? So all the great scientists, all the scholars, scientists, literatures, all attended the Hindu school. And then it was in this nice neoclassical kind of building. So this building doesn't exist anymore. Now we have this. Okay. And so anyway, at this school, Bose was always good at mathematics. So now there was a legendary mathematics teacher, Upendranath Bakshi. I couldn't find a photograph of him, so I've given you a cartoon instead. So Bakshi taught him specially, and he was a very great favorite of Bakshi. It is related that once he gave this young Bose 110 out of 100 in his geometry examination. Why? Not for solving this problem. I've just given it to you to remind you how complicated geometry riders could be. But Bose had not just solved all the problems in the exam, but he had solved each of them in more than one way. So, there was no help for it but to give him more than 100. And Bakshi was very proud of this thing. He said, one day this young protege will become a Laplace or a Cauchy. Of course, he didn't become a Laplace or a Cauchy, but he did something great in his own right. Then, this is how College Square used to look in those days. This was the University Senate Hall. It doesn't exist anymore. This is High School, which still exists. This is the Presidency College, which still exists. This part was Hindu School, which I have shown you how it looks now. So, in 1909, Satyendra Nath Bose entered the famous Presidency College. Again, this was the home of the Bengal Renaissance. This was shortly after, this was actually at the time when De Rosier and others were teaching there. No, they had gone, sorry. This was after the legacy of that people continued. And there, he graduated in the mathematics department. So, he had a galaxy of brilliant teachers in the Presidency College. So, English was taught by Percival, Madan Mohan Ghosh, Prafulla Chandra Ghosh, who were reputed to be great teachers in those days. Mathematics was taught by C. E. Cullis and D. N. Malik. Physiology was taught by S. C. Mahalanobis, who was the uncle of Prashant Mahalanobis, the famous statistician. Chemistry, famous Acharya Prafulla Chandra Ray. And finally, physics, the redoubtable J.C. Bose. So, taught by very, very good teachers. So, in 1911, he passed his intermediate in science and passed out with an honors in mathematics in 1913. Then, so I will show you two nice pictures. One of Bose, he is here with P.C. Roy, and this is J.C. Ghosh, and I'm not sure I can recognize the others, but this is one. So, this is P.C. Roy with his favorite students. And here's another picture, similar picture of J.C. Bose with his favorite students. And Bose is here, of course. This is Saha, J.C. Ghosh, D.M. Bose, N.R. Sen, and others. So, in 1915, he won his MSc in a subject which used to be called mixed mathematics, which is essentially what we call applied mathematics today. So, you want to know the marks? All right. So, 100 and 100 in one paper. In those days, remember, to get 60 was considered a lot of marks. So, this total comes to, out of 800, is 92%. And you may be asked, which paper did he get 100 and 100 in? Interestingly, it was physiology. So showing you that Bose certainly had a great memory. All right. So of course, with such marks, he won the gold medal of Calcutta University. But having done so, after all these heroics, while studying for his MSc, Bose got married. And his bride was Ushabati Ghosh. You see her here at the time of marriage. She was the daughter of a prominent Kolkata doctor. So a rich man. And as you see, this is one of their wedding photos. And a rich man, you can see from the amount of jewelry which the bride is wearing. And the point is that Bose refused to take any dowry, which was customary in those days. It was also customary for a rich father-in-law to send his son-in-law abroad for higher studies, which again Bose refused. But all he said was that I have about 200 friends. Can you invite them for the wedding? So that was actually done. So they came to the wedding feast. In fact, Ushabati, who was 11 years old at the time of her marriage, again not surprising in those days, she ultimately had 9 children, of whom 7 survived into adulthood. Again, normal for those times. And Mrs. Bose apparently was a very gracious and uncomplaining hostess to her husband's diverse friends. So so out of these 200 friends, a fair fraction would always be dropping in. And then Bose would say, oh, so-and-so will stay to dinner, so-and-so will stay to lunch. And poor Mrs. Bose had to cook up something in a hurry to accommodate them. But apparently, she was always gracious and uncomplaining about that. Here you see a picture of Bose later in his life this is Mrs. Bose. This gentleman is clearly Bose's son, but the rest of all is extended family. Now, let's go back to that period. His MSc passed with flying colors. Now the Satyendra Nath found himself unemployed. Okay, it's a common phenomenon. But having passed it, what could he do? He was too good a student to go and become a clerk in an office. Okay, but he was a married man now and he would soon become a father, so he had to start earning. If you are a good student, what do? You do private tuitions. So he did several, but among them, in fact, the most famous student didn't become a scientist. The famous student was the young heir of the Gauripur state, which is now in Assam. His name was Pramathesh Chandra Barua. And he was one of the early icons of Bengali cinema, certainly the first person to play Devdas. Okay. And what was Bose's fee as a tutor? 200 rupees per month. Now I'll come back to this figure soon. So it was actually it was literally a princely figure in those days. All right, so then Bose saw an advertisement for teachers by the Bihar Educational Service. So Bihar had been created out of Bengal. When the partition of Bengal was annulled in 1911, Bihar and Orissa were carved out as separate states. So there was a new educational service, but his application was rejected as he was deemed overqualified. So the Bihar government at that time didn't want their teachers to know too much. Okay. So what to do? Then he thought, okay, since I'm overqualified, let me get some more qualification. So he tried to start a PhD in mathematics with the noted Professor Ganesh Prasad, who had just come to Calcutta from Allahabad University. But very soon, Bose fought with Prasad. The reason is that Ganesh Prasad was very critical of Bose's teachers, who had taught him mathematics and things, and said, these guys don't know anything. Okay. And Bose would stand up for his teachers. So eventually, Prasad got fed up with him and said, you may have done well in the examination, but that does not mean you are cut out for research. Perhaps many people in the audience have heard similar things. Okay. So Bose gave up that attempt, but then came a lucky break. What was that lucky break? Sir Ashutosh Mukherjee, who was a mathematician turned a lawyer and a judge, he became the second Indian Vice Chancellor of the Calcutta University in 1906. So being a mathematician by training, among other reforms, he started PG departments in physics and chemistry. Mathematics already existed. The physics department was started in 1915, the very year Bose and his friends were graduating. Okay, so what did he start it with? It's an important question at all stages. Sir Ashutosh persuaded two of his rich lawyer friends to donate generously for these new departments. So Sir Rashbihari Ghosh gave him 21 lakhs. Sir Taraknath Palit gave him 14 lakhs. Just to put it in perspective, this was in 1915. In 1913, Ramanujam had written his famous letter to Hardy saying, I am a poor clerk and my pay is 20 rupees a month. Okay, so it also tells you how much money lawyers made, at least in those days. Okay. Now I should translate it into modern terms and assume that Ramanujam gets what a clerk will, junior clerk will get today. These donations amount to something like 250 crores and 170 crores on this. I wish TIFR could find such donors. So anyway, so with these, so now with this money, now Sir Ashutosh then built up a truly stellar physics department. It's one of the greatest departments which this country has ever seen. So where were they? There was D.M. Bose, Ghosh professor. C.V. Raman joined as Palit professor in 1917. Mahalanobis, who was in Presidency College, was an adjunct member. He came and gave lectures. And there was this bunch of young lecturers, Meghnad Saha, Satyendra Bose, and then S.K. Mitra. So he's been a little bit in the news recently. You might have seen that, because Chandrayaan has photographed a crater on the moon, which is named Mitra after him. And B.B. Roy was a great spectroscopist, perhaps more forgotten today than any of the rest. Okay, so what salaries did these people get? That's interesting. So Bose was paid 600 rupees a month. Raman was paid 1,000 rupees a month. Okay, and the lecturers were paid 125 rupees a month. So remember, given that poor Ramanujam was being, literally poor, Ramanujam was being paid 20 rupees a month, this was a very, very handsome sum. And you may be interested also to know what they taught. So Mahalanobis taught mathematical physics, D.M. Bose taught atomic physics, Raman taught waves and optics, M.N. Saha taught quantum theory, Bose taught relativity, Saha taught radio physics, which really meant electromagnetic theory, and Roy taught spectroscopy. So that was this department, and Bose was taken so as a young lecturer to join this. Now, while all this was happening, other things were going on in the rest of the world. So the First World War was raging in Europe, and the youth, including many, many promising scientists, were all taken up in this hideous business, which sort of is unfolding before you, including two very, very famous scientists, Henry Moseley, who was killed in Turkey, and Kurt Schwarzschild, who was killed in Russia fighting. So let's stop this. So, but things happened. It mattered for India. Why did it matter? Because during the war, Indian nationalism, which had been mostly arguments and petitions, assumed a militant form. So it started with the Ghadar conspiracy, well, quote unquote conspiracy. And so this is the first meeting where the Ghadar movement was started in a hall in Los Angeles. And its offshoots aimed to overthrow British power with arms smuggled from Germany. So that was the point. Germany was at war with Britain, so they would give arms. So some of the leaders, Bhai Parmanand, Lala Hardayal, who worked from US and Canada, Rashbihari Bose, who worked inside England, and the actual foot soldiers, Pingle, Kartar Singh, and Jatin Mukherjee. All of the people below here lost their lives. And whatever, but of course it was not well planned. The British were able to overthrow it. So some people were sent to the Andamans for as labor, and the rest were put up against a wall and shot. Then, but this nationalist movement struck a deep chord in the mind of the young Satyendra Nath Bose. So it was around this time, a little earlier, that the first Indian flag had been designed by Madame Kama and Savarkar. And Madame Kama actually went to Stuttgart, and this is the first version. Some relics of this are there in the present flag. This is the first flag of Free India designed. And Bose, associated with the Bengal School of Revolutionaries, he had people coming and going to his house all the time. And even as a BSc student, he had taught in an evening school for adults. So the idea was to wean people away from the British schools. And so did Meghnad Saha. In fact, Meghnad Saha had already been expelled from school for boycotting the governor's visit. So all the boys who didn't come when the governor visited were expelled, and Saha had to go to a different school, lost a couple of years. And they were very close friends. So the result is, so that means they were very, very. And then they had another friend and their colleague in Calcutta University, Satyendra Nath Bose, ASET Ghosh. He was so much involved in the revolutionary activities, which meant, violent activities, that he actually had to flee from India to save himself from the colonial police. So the university became a person short. And then in 1919 came the Jallianwala Bagh massacre. I'll leave you to watch this clip, which is from Attenborough's film on Gandhi for a minute or so. So it's fitting to watch this. This, of course, is General Dyer. Okay, so the result of this was that it marked the beginning of the end of the British Raj. Now, Indians in their millions came out in the open to demand freedom. Okay, the non-cooperation movement had unprecedented partition, as you must have read. Now, though he was sympathetic to the national cause, Bose did not participate in the non-cooperation movement. In fact, his father had told him, look, you are a married man, don't lose your job, so don't participate explicitly in this. Okay. In fact, Sir Ashutosh, the VC, he didn't approve of what he called disorderly agitation, which was like, burning British things and so on, a boycott movement, Swadeshi, burning the British books and so on. But 80% of the students of Calcutta University responded enthusiastically to the call of Gandhiji, and they boycotted their classes and publicly made bonfires of foreign goods. All this is relevant, I'll come to it in a moment. In retaliation, the government of Bengal, so what does the government do when they don't like what you're doing? They threatened to withdraw financial support. And unless there were 8 humiliating conditions, which were, so the word humiliating is from Sir Ashutosh, unless these conditions were met, which would give the Sarkari officials complete control of the university's internal matters. Nothing changes, does it? Sir Ashutosh fought this tooth and nail, but by 1924, he was dead, and another person was appointed who was pliable and who agreed to all the conditions. However, in 1921, so if the funds went away, among the jobs threatened was that of Bose. So he found his job at stake. And of course, he would not get sympathy because he was already marked by the police as a sympathizer of the national movement. So it was at this point that he made his fateful decision to move to the newly founded University of Dhaka. This is the famous Curzon Hall of Dhaka University. And Sir Philip Hartog, the new vice-chancellor, he had come to Kolkata on a headhunting mission, what we call today a headhunting mission. So he handpicked Bose and a few other people like J.C. Ghosh and others and persuaded them to move to Dhaka. So this is a sort of grady picture of Hartog. Salary, 400 rupees a month instead of 125, and 50 rupees increment per year to a total of 1,200 per month. Who can resist that? Okay. So Bose decided to leave Calcutta, where he had been born and brought up, and take a train and take a boat and go on the rivers of East Bengal, and he ended up in Dhaka. Of course, Meghnad Saha hailed from that place, but for Bose it was a first. Now, once he reached Dhaka University, he discovered that the life as a pioneer is always hard. So writing to Saha in 1929, this may not be visible from the back, but I'll read it out. It has been well over a month since I moved to your part of the country. Work has not yet started. Your Dhaka College had quite a few things, but due to utter neglect, they are in a bad way. Perhaps I need not elaborate. On the table of the sahibs are scattered lots of nickel prisms, lens and eyepieces. It would require a lot of research to determine which one belongs to which apparatus. We do suffer from lack of journals here, but the authorities of the new university have promised to place orders for some of them along with their back numbers. They are talking about having a separate science library. So those were the initial conditions. So Bose taught thermodynamics and electrodynamics, and at the same time he had to set up laboratories and buy books for the library. So he was kept very busy. Then 2 years later came a big jolt. Again, due to bureaucratic wrangling with the Bengal government, Dhaka University faced a financial crunch. Among other forced economies, Bose's regular appointment, that all those nice golden figures, were changed to a 1-year contract on fixed salary with no promise of continuation. She was told, okay, we'll give you a contract, 1 year, you're getting 400 rupees, you get 400 rupees. After 1 year, we'll see. So Bose fought hard to keep his job. He was very upset. He wrote to the Vice Chancellor, I shall be in Dhaka after the vacation and shall stay on pending the decision of the Executive Council, to which he had appealed against. But I am afraid that I can't give any undertaking to serve till 8th October. If the university authorities persist in their unjust decision, I shall have to seek for a job elsewhere. Okay. So, of course, the Vice Chancellor was not taking this from a junior person. So he wrote back sharply, saying that you're getting lots of money anyway. But he was a fair-minded man. In March 1924, he chaired a committee which resolved the following. Mr. S.N. Bose to continue his work as reader till the end of the present session on his present salary. Mr. S.N. Bose to be granted 2 years study leave as from the beginning of September 1924. Mr. S.N. Bose to receive a total advance of 13,800. So the university would pay for him to visit Europe and stay on. So this was a huge sum of money compared to what he was making, 400 rupees a month. But at the same time, it was just barely enough for him to take care of his travel and stay there. Now it was while all this tussle with his job was going on that Bose wrote his famous paper on blackbody radiation. So I'll just take a sip of water and continue. So we move back to science. So this doesn't look like science, but during the Durga Puja of 1923, so Meghnad Saha came home to his village near Dhaka, and since his great friend was very close by, he naturally visited his dear friend Satyendra Nath Bose. The two had much to discuss, okay, as old friends do. Now Bose, who was teaching thermodynamics of blackbody radiation, he complained that this theory of Planck is hard to teach because students keep asking awkward questions. It shows you that he had good students. So they were asking awkward questions, and he said, it's difficult to teach that. Now remember, you've seen the condition of journals at Dhaka University. Meghnad Saha had recently moved to Allahabad University. You see the famous tower of that. So Allahabad University did get more journals, so he had some access to them. So he informed Bose about the papers of Pauli and of Einstein and Ehrenfest. Apparently, he had also taken down some notes by hand in those days, no Xerox machines. So he wrote down some notes and he showed them to Bose. This is what Pauli has said and this is what Einstein has. So I've told you about those papers. Okay. So let me remind you that Lorentz and Fokker at separate times had shown that suppose you have a mix, a cavity, in which let's say the red particles are the material particles and the blue ones are photons. So the moment transfer between free electrons, let us say, and radiation, it cannot take place through radiation pressure alone. It's just not enough to give the proper distribution. And then Pauli showed that instead of radiation pressure, if you use Compton scattering, which had just been discovered, then that can happen. So much more is transferred when Compton scattering happens. But then, of course, using this momentum transfer, he used Einstein's 1917 derivation, and as you saw with the nonlinear term, which also violates causality in the sense that it causes for a requirement of the future density. And Einstein and Ehrenfest, as I said, extended this calculation to atoms with discrete energy levels. So when the celebrations were over and Saha had gone back to Kolkata or to Allahabad, Bose decided to sit down and treat the photons purely as particles, forming a gas just like molecules of hydrogen, oxygen, etc. do. Now this was his real departure, and this is what we'll see what happens. Of course, let me quickly take you through this. The statistical behavior of gas had been worked out by Maxwell and by Boltzmann, and giving the standard Maxwell-Boltzmann statistics we have been mentioning so often. So let's just take you through it. So the phase space of a gas is a multidimensional space whose coordinates are all the coordinates and all the momenta of the n gas molecules. So if you take the position, the coordinate, x coordinate, and the momenta of just one gas, then you form these little cells. This is a small range in x, a small range in P. So, they form what you call a phase cell. And you imagine a phase cell. So, if the volume of this is, let us say, delta, it is a tiny little cell. So, if it is 3 dimensions, you will have delta cube for each particle. Okay. So, we go ahead with this. So, Boltzmann had showed that the number of such phase cells lying between an energy E and a little change term E is proportional to that change, of course, but also with this factor, okay, which you get from there, and divided by delta. That is the number of phase pairs. So, this is the total phase volume and divided by the number of volume of a phase cell. So, it gives you the number of phase cells. Then you calculate the statistical probability of distributing small n number of particles among these cells. For this, you simply count the number of configurations created by putting small n particles among capital N different phase cells for this energy range. So, this is equivalent to the following situation. So, imagine each of these boxes is a certain delta E, range in energy. And inside each of these boxes, there exists this number of compartments. Okay. Now, you have taken the particles, you are distributing a set of colored balls which go into these different compartments. So, how many ways can you do this? So, this is a standard problem in combinatorics, and the answer is simply this. It is the number of boxes, or number of compartments to the power of the number of balls divided by factorial of the number of balls. Okay. And when we take all the energy boxes, then you have to multiply these probabilities. So, you multiply by the total number and also by the number of possible that you could exchange things between themselves. What is n? Is the total number of particles in all the boxes. So, just the sum over all them, which can be an integral also if it is continuous. So, you can now find the entropy of this. So, you found the number of configurations. You can find the entropy by using the famous law of Boltzmann, which is the Boltzmann constant into log of the entropy. So, in this case, you plug in this formula. Now, the second law of thermodynamics tells us that when the gas is in equilibrium, the entropy must be maximum. So, that means the distribution of particles must be such. So, these n's must have a distribution such that this quantity is maximum. So, that is a simple problem in probability theory. Of course, subject to two constraints, the total number must be fixed and the total energy must be fixed. So, when you do that, you will get this following distribution. The number, this is the distribution which this is known as the Maxwell-Boltzmann distribution. Okay. Notice that there is delta in this. So, the delta has cancelled out. So, now you can happily take the delta to 0 if you want to. So, you do get back the energy and momenta continuum if you want. For an ideal gas where the particles do not interact, E is half mv squared, everyone knows this. So, if you plug this back, you get the famous Maxwellian form, which has been tested in several experiments. You get formulae like that. Now, for photons, so Bose made 3 very crucial physics assumptions, not mathematics, physics assumptions, and the assumptions he made are the following. So, I'll describe 2 of them first and then I'll come back to the third later. So, the first assumption, he took this phase cell to really have an area H instead of delta. So, that means delta x into delta p is order H. Looks familiar? Indeed, this is exactly the uncertainty principle of Heisenberg, and remember this was 1923, so 2 years before Heisenberg thought of it. Heisenberg had very good reasons of thinking about it. I don't want to take away any credit, and Bose certainly did not think of it in the same way as Heisenberg had done, but he had used the result.
Why? Why did he do this?
Good question. All right. I'll answer you in the words of Bose, we'll come to it. But he did assume it's H. And he was very proud of it. Okay. The second assumption, he assumed that the photons are not just identical, but indistinguishable. This had been done by Nathanson, but I don't think Bose had seen Nathanson's paper. But this can only happen if you have wave-particle duality. Again, I'm not saying Bose thought of it in the same way as De Broglie did. But what it means is if they're indistinguishable, they are not colored balls. They're all identical. So if you exchange this one with this one, nothing changes. So you have to do the combinatoric problem in a different way. Okay. So it has been done afresh, take into account the fact that interchange of the balls in the boxes and partitions gives the same configuration. Okay. Now this is a mathematical problem which has a long history. S.N. Bose was not the person who solved it. In fact, it had been done by many mathematicians, including Pingala in the 2nd century BC. and by several others, including very famous names Pascal Leibniz. So, what the earlier people were looking for is the number of ways number of words you can construct with a given number of letters, with the letters being possibly repeated, which is essentially the same problem. So, therefore, Pingala in his work on prosody and Omar Khayyam and is there in the Lilavati also, and Rabi Ben Ezra, who are concerned with how to write poems and so on, had all this in place. Now, Bose must have immediately known this answer. There is no mathematics which he done. Why is that? I'll give you the proof of that. So, Bose apparently had worked through this entire book called Algebra by Todd Hunter, which is particularly has difficult problems in it. It's but it was the popular book in those days, so published in 1880. And the answer is on page 536 to find of that. So, since Bose had worked through it, he must have immediately known where to find the answer. And therefore, that's the answer. The number of configurations given by this particular formula, factorial of this quantity, number of states plus number of particles minus 1 and factorials. Okay. So, when you take, I'm doing exactly what I did for Maxwell. You take all the energy boxes, it becomes a product over all the energy boxes. Then, if these photons are in an enclosure, they are being absorbed and emitted all the time, so the total number is not fixed. So, this is a new assumption. Okay. This is different from what Maxwell and Boltzmann did. But now you do the same thing, find the entropy using the Boltzmann. In this case, you put this formula in instead of the earlier one. Second law tells you that same thing, entropy must be maximum, distribution must be such to maximize this quantity. Subject to the same conditions? No, not the same conditions. Total number is no longer fixed. Only the total energy is fixed. Okay. Once you do this, it gives you this distribution. So, you already see the denominator has the Planckian form. Okay. Just by assuming this indistinguishability. So, all this arose from taking the photons to be indistinguishable. Now, Bose's calculation of this number n was also novel, and so this is the equipartition law. Now, how to calculate what you call the Rayleigh-Jeans formula or the Rayleigh-Jeans law, a number. So, this was also novel. So, what he did was for photons, he combined Planck's law and Einstein's mass-energy relation to write this is the Einstein mass-energy relation for a massless particle, this is the Planck's law. So, if you combine them, of course, nu is c by lambda, so you get p is h by lambda, which is de Broglie's relation. So, he used it without giving it the same meanings as de Broglie did. So, if you take this, the number of phase cells is given by this quantity proportional to the volume, and therefore, if you take it by, so you replace this, so you write it in terms of momentum, okay, just a momentum volume, a sphere, and replace it in terms of nu, and then taken per unit volume, he immediately got the same number of photons. This is the Rayleigh number. And when you plug in the statistical distribution which he had found, the result was this. Okay. Hence, the average energy times h nu times this. So, it's this formula. So, if you compare this with Planck's distribution formula, you find that everything matches except a factor of 2. Okay? Everything matches except a factor of 2. This is where Bose made his third physical assumption. He assumed that the photons spin around their axes like planets, either clockwise or anti-clockwise. So, there are two angular momentum states associated with each photon. Okay. So, he had this factor of 2. Now, of course, this is the concept of intrinsic scale. Again, 1 year before Uhlenbeck and Gauss-Schmidt proposed it, which was in 1924. Again, they had a wealth of other reasons to propose it. So, Bose had just put in this number saying, okay, this is angular momentum states. What else can it have? Naturally, I'll come back to this again. Bose did not realize how far-reaching these assumptions were. But he did realize that he had done an important piece of work. Okay. He had derived the Planck formula without requiring anything about the oscillators in the walls. This was purely a property of the photons. Okay. And so, he wrote it up in a modestly titled paper, Planck's law and the light quantum hypothesis. Okay. Well, many people write modestly titled papers. And So here I am showing you a little bit of Bose's handwriting, Bose's calculation. This is not the manuscript of that paper, which is lost, but this is a calculation he wrote up later and gave to Einstein, and it's been found in the Einstein archives. So full of confidence, towards the end of 1923, Bose sent his manuscript for publication to the well-known British journal, the Philosophical Magazine. So that was the most popular, sort of other than Nature, it was the important journal where you send these kind of results. Not surprisingly, the journal sent his paper back. After 6 months, they sat on it for 6 months and sent his manuscript back with a curt note saying they could not publish it because the referee report was negative. Familiar phenomenon, you are all familiar with this, but except that in those days they didn't even bother to send the referee report. Okay, so paper was rejected. So now in June 1924, with his job only guaranteed till September, Bose took a bold step or a desperate step. He sent his manuscript to Einstein. Okay, so he wrote the following letter to Einstein from the physics department, 4th June. And he said, "Respected sir, I have ventured to send you the accompanying article for your perusal and opinion. I am anxious to know what you think of it. You will see that he tries to derive this coefficient in Planck's law independent of the classical electron." So he is proud of that derivation. Okay. And then he says the ultimate element in the Planck space has this h cube volume. So he is proud of that. Then he says something interesting. He writes, "I do not know enough German to translate the paper. If you think the paper worth publishing and so on, you could help it in Zeitschrift für Physik." The point is that Bose did know a lot of German. In fact, he knew enough German to have translated Einstein's papers into English. Okay. So there's a volume which had come out in 1919, so by Saha and Bose, and with Base, which came out in 1919, in which, so if he knew enough science to translate Einstein's papers into English, then clearly he knew enough to translate. But I think he was just being modest. Sorry? Good question, but yes. So I don't know, perhaps he was not confident. But anyway, Einstein realized that at least he could read German. So Einstein's letter to him was in German. Okay, though Einstein knew English perfectly well. So that's Einstein's letter. As you can see, it's in German, and I'll translate it for you. He was supportive, but at the same time, he was defensive of his own work. Okay, he says, "Dear colleague, I have translated your work and communicated it to," so he did actually into Zeitschrift für Physik, and it did come out. As you see, so it's Planck's law and the light quantum hypothesis by Bose. So Einstein didn't know which part of his name to use. So from Dhaka University, India. And then he says, "It signifies an important step forward and I liked it very much. You are the first to derive the factor quantum theoretically." That's this Rayleigh-Jeans factor. It's a beautiful step forward. So he likes it. And then, but see, he doesn't talk about, he says polarization factor. I'll come back to this again. Okay, so he got support from Einstein, that's the important thing. And then he added a note of support at the end, mentioning that this was indeed important work. So he says, "Translator's remarks," that's what this is. "In my opinion, Bose's derivation signifies an important advance. The method used here gives the quantum theory of an ideal gas, as I will work out elsewhere." So notice that he neither invited Bose to collaborate or take this work ahead, nor did he ask Bose to visit him at Berlin. He was going to do it himself. Not only that, whereas Bose had these ideas of angular momentum, he didn't like that, so he replaced it. So editors could happily replace things on their own in those days. So he replaced it with the word polarization, which is meaningless for a particle. Okay, and then he says, if you take this, not only that, in his earlier letter, it is he who put in polarization, and he there says, because of this polarization factor, not wholly rigorously. Okay, so he did this much messing up with Bose's paper. So in 1970, Jagdish Mehra, the well-known historian of scientists, interviewed Bose. So I'll try to answer your question. How do you do it? I had no idea what I had done was really novel. This is what Bose said. I thought that perhaps it was the way of looking at the thing. I was not a statistician to the extent of really knowing that I was doing something which was really different from what Boltzmann would have done from Boltzmann statistics. Instead of thinking of the light quantum just as a particle, I talked about these states. So he had vague ideas of quantum mechanics, which we do now talk about those. Then he says, somehow this was the same question that Einstein asked when I met him. So Gautam, you can be happy that you asked the same question that Einstein did. Okay. How had I arrived at this method of deriving Planck's formula? Well, I recognized the contradictions in the attempts of Planck and Einstein and applied the statistics in my own way, but I did not think that it was different from Boltzmann's statistics. So it's not very illuminating, I think. But to go back to Sherlock Holmes again, so when Watson asked Sherlock Holmes, how did you deduce this? Sherlock Holmes said, it's easier to do it. If somebody asks you that 2 and 2 is 4, and you ask you, how do you know that? It's quite difficult to answer. So people have flashes of intuition. Anyway, at least Bose's work had won some recognition, but later the only one who afterwards stood up for his spin idea was Raman. In a paper with Bhagavantam, he had written, we understand from a personal communication by Professor Bose that he had assumed that these 2 states of angular momentum and so on, wave factor 2. However, we don't have the manuscript, so we don't have any proof. So Einstein's postcard did serve to smooth the path to getting visas for Bose's Europe trip, which was financed by the university. So everywhere he gave a copy of Einstein's Europe trip. And in fact, for the German visa, the fee was waived. So this is what a British Indian passport looked like in those days. And so he got that. So finally, but yes, I should tell you this. So the Vice Chancellor, Hartog, wrote to important labs in England. So of course, he wanted to send him to the UK, to England. So he had sent out strong letters of recommendation to 2 famous labs. To Sir William Bragg, the elder Bragg, at the Davy Lab in London. So we have no records that Bragg replied at all. Okay, he may have replied, but no records exist. But of course, he didn't take Bose. And Lord Rutherford at Cavendish Lab, he sent back a regret saying, we don't have space. So that's the standard answer when you have unwanted people wanting to come and work. Okay. But nevertheless, the French were more accommodating. And so in September 1924, Bose set out for Europe. He was the last of his illustrious classmates and colleagues to do so. So Saha, then B.B. Roy, Mitra, they had all gone to Europe already and worked there and settled there. And one of the reasons was, so that's something which touches Bombay, so I should tell you this. There was a scholarship in those days called the Premchand Roychand Scholarship. So Premchand Roychand was a Seth from Bombay, cotton mills and so on, and he had given this scholarship. So today people don't remember Premchand Roychand so much, but his mother was Rajabai, and the Rajabai Tower was actually built with his money. So the Premchand Roychand, so these people had all applied for the Premchand Roychand scholarship. It gave them enough, they add a little from other sources, and you could spend a couple of years in Europe. Bose had also applied, and he was called by Sir Ashutosh, saying that, you have made this application, asked me to forward it. But then he said, I'm sorry, son, you can't be, because the conditions specify that you have to be a bachelor. And I still remember the excellent fish curry I had at your wedding. So Bose couldn't get that. But anyway, later Dhaka University financed him. So on November 18th of that year, Bose reached Paris. Now, why Paris? First of all, in 1923, one Dr. R.L. Dey from Dhaka University had already been sent to work with Madame Curie at her laboratory in the Radium Institute at Paris. And Bose's mails were being sent on to Dey, and he needed to pick them up. There was also some cheap accommodation to be held at the Indian Students Association, and some of Bose's old revolutionary friends were there, had escaped from India and were sitting there. So Bose was advised that if he wanted to work in Madame Curie's laboratory, he should first meet with Paul Langevin, who was well known to be Pierre Curie's student and close to Madame Curie. So Langevin had read Bose's paper and was suitably impressed. So he welcomed the young Indian with open arms. And from then onwards, for many years, he was a friend and mentor for Bose. Learning that Bose was interested in both crystallography and radioactivity, he gave him letters of introduction to both Madame Curie and crystallographer Maurice de Broglie, who was the elder brother of Louis de Broglie. So he went to meet Madame Curie. This is a real footage of the real Madame Curie. So you see her short hair, and this was because she was already suffering from radiation sickness, which killed her. Okay. Now this famous lady, she greeted Bose warmly and said, since you are coming from Langevin, I will certainly allow you to work in my radium institute, with a but. Then she said, she herself spoke perfect English. She asked Bose to wait till the new year and said, you should learn French, because your predecessor, Dr. Day, didn't know French and faced a lot of difficulties, so you should learn French. So Bose, apparently, he was so overawed by meeting this lady that he forgot to tell her that he had already known French for 10 years. And he could read, write, and speak it fluently. In fact, he had spoken to Langevin and others in French. But he was too overawed to say anything. So he resigned himself to work for the time being in the laboratory of Maurice de Broglie. This is his picture. Okay, who was a very well-known crystallographer in those days. Then days slipped into weeks and weeks slipped into months. So Bose remained in Paris working in the Broglie lab, and from the new year 1925 at the radio. From the new year, Madame Curie had promised, so he was allowed to work there. He reveled in the atmosphere. He started learning experimental techniques from these experts and discussing theory with Langevin and Louis de Broglie, who would visit his brother's lab, and at the same time enjoying the company of Indian students and revolutionaries. He also made friends among the Europeans, especially Bertrand Zadokhan, a young cardiologist, you see him arm in arm with Bose, and his pretty sister Jacqueline, who also remained a lifelong friend, were to remain always. And she actually later, so Zadokhan died early, but she visited him later, even in Kolkata. So meanwhile, Einstein had translated and published a second paper by Bose, sent shortly after the first one, in which Bose had considered ideal gas in statistical equilibrium with radiation. So he was looking at the same problem they had done, and found that again, if you use the same kind of statistics, just distinguishable versus indistinguishable, you will find that you get the Planckian distribution for photons and the Maxwell distribution. No interactions needed. So now if you're curious what this Ramana is, that's the suburb of Dhaka in which the university was located. So now, of course, it's not a suburb anymore. So this was already there. Bose wrote to Einstein, dear master, I have been granted leave by my university for 2 years and so on, and I will be glad if you grant me permission to work under you, for it will be long cherished hope. So Einstein wrote back saying, fine, I'm glad I shall have the opportunity soon of making a personal acquaintance and whatever. And then I am not in agreement with your basic principles. So he has published the paper, but again he's defending his own work. Okay. And while he was doing this, he was feverishly working on Bose's idea. Okay, without telling or inviting Bose to join him on this. In July 1924, he had worked out the statistical distribution of the atoms in a monoatomic ideal gas, which we would now call a massive boson gas. So this paper came in July 1924. And then the other famous paper, the quantum theory, with almost the same title, but this one talks about the Bose-Einstein, what is now famous as the Bose-Einstein condensation. So that's the single author papers by Einstein, completely using Bose's techniques, but citing Bose, but no invitation for Bose to work on it. He also found in Bose's statistics the missing piece in his own theory of the specific heat of solids. So I've run far beyond my time, so I'll just skip through this. But essentially, Einstein was able to explain this, the variation in the Dulong-Pettit law, and he only had to require the oscillators to be bosons. Okay, bosons. So Bose, today we call them photons. Okay. So in all these years, Einstein scrupulously acknowledged that the statistical method was Bose, but he was not going to share the glory of these further discoveries with a guy whom he had never met. In fact, it was Paul Dirac who made Bose immortal. In 1926, he coined the expression Bose-Einstein statistics and Fermi-Dirac statistics. Notice that here he's gone non-alphabetic to put his name afterwards. Okay. And in excess of modesty, he called these particles Bose fermions. So if these are fermions, these have to be bosons. The names have stayed ever since. However, Bose was never bothered about Einstein's selfishness. To him, Einstein was the master. So after a whole year in Paris, he finally was able to move to Berlin. This was the Kaiser Wilhelm Institute for Physics, and Einstein was then the director of this. So here's a little footage of the great man himself. Of course, probably at the end of the day. So there were lots of other people in Berlin, famous people, Max Planck, Walter Nernst, Otto Hahn, you can go through the list, but it all revolved around one person. Okay, so he was the star of the group. There were other people who were great in their own right. So Bose came to know all these people and became good friends with them. In 1925 came the new quantum mechanics, the papers by Heisenberg, Born and Jordan, then Heisenberg, Born and Jordan. So this had come. And at that time, of course, a lot of excitement about this. So Bose wrote to Jacqueline Zadokan. He says, every physicist seems to be quite excited in Berlin the way things have been with physics. First on the 28th, Heisenberg spoke in the colloquium about his theory. Everyone is quite bewildered, and there's going to be very soon a discussion of Schrödinger's papers. Einstein seemed quite excited about it. The other day, coming from the colloquium by train, we found him jumping in the same compartment where we were, and forthwith he began to talk excitedly about the things we have just heard. We were all silent, but he talked almost all the time, unconscious of the interest and wonder that he is exciting in the mind of the other passengers. So you can see excitement about it. And so Einstein suggested to Bose two problems. He suggested but he was still thinking in the old lines, whether their new statistics implied some subtle interactions between the photons themselves. How could the transition probabilities of spontaneous and stimulated emission be derived in the new quantum mechanics? Of course, we do it regularly today, but it was an important problem in those days. For some reason, Bose did not make any headway in either of these problems. What he did instead, maybe he didn't like it, maybe whatever, he started working in Hermann Mach's crystallography lab, continuing the work he had been doing with Maurice de Broglie. He visited Einstein regularly and had all manner of animated discussions with him, but these two problems remained unfinished. In mid-1926, he came back to India. In fact, Bose did not publish a single paper during his 2 years in Europe. While in Paris, he did write a third paper on radiation and statistics, and this had a lot of interesting ideas in it. And he says that sometime that quantum theory is to be brought in line with generalized relativity theory, which people are still trying to do. And then, in fact, it seems from what he said later that this paper contained the seeds of what Dirac later developed as second quantization, and which was developed later into quantum field theory. He had some of those ideas, but the manuscript is lost, so we will never know for sure. We just remember what he told people later. And working with Einstein was not easy. A close friend of Bose has described how many letters he opened up a little. He said one day he was reminiscing about his Berlin days. Einstein had given him a problem to solve. Satyendra told me, I thought about it for 3 days and then I went to see him with my solution. Einstein said, well, this is not wrong, but not the way I want it. This clue does not open up any new possibility. Please don't waste my time with such trifles. Okay, so I would say extremely rude. The truth is that the 46-year-old Einstein did not like being proved wrong any more than anyone else. And his intense creative paper was actually over. In fact, these were his last great works. And Bose himself did not publish in theoretical physics till 1939. This was 1924. So he came back in 1926. So for 13 years, he didn't work in theoretical physics. So now the last part of my talk, I'll just talk about the sage. And this will run through the rest of his life in a sort of panorama. The milestones. 1926, he returned to Dhaka to a hero's welcome. Reference letters from Einstein, Lajova, Hermann Mach. After all, he didn't have a PhD. He was appointed professor and head of the Department of Physics at Dhaka University. So the same place which had given him a 1-year contract was now willing to give him a lot of honors. After 1 year, he was also made Dean of Science. He now set up laboratories in chemistry, optics, and crystallography and started publishing in these areas. By 1938, Calcutta University offered him the Palit Professor's chair, which had been vacated by Raman, and he rejected it. Instead, Meghnad Saha took it. So what are the kind of things he did there? So you see, electrochemistry, spectroscopy, beryllium spectrum in the region something. This is on the Mahalanobis measure, work on statistics, pure statistics. Anomalistic diagnostic constant of artificial ionosphere, so again work on radio physics, perhaps with his friend Sachin Mitra. Then in 1939 comes this studies in the Lorentz group, in which he is one of the first people to propose using what we call today the two-component notation. complete solution of the what you will recognize as the inhomogeneous Klein-Gordon equation. So, now he is back to theoretical physics again, but not having abandoned chemistry, reaction of sulfonazides with pyridine salts and so on. But also note on Dirac equations, the Zeeman effect. So, this is really a solution of the hydrogen atom problem with the Dirac equation. In 1945, he was again offered a chair at Calcutta University and he left Dhaka forever. Now, Bose loved Dhaka, but at that time the atmosphere in Dhaka was really becoming bad with communal riots and deaths every day. So, he had this feeling of insecurity and decided to come back to Kolkata. In 1947 came independence and the second partition of Bengal, so now Bose could never go back to Dhaka. But while others of his contemporaries became nation builders, okay, Maulana Base, Bhabha, Sarabhai, Meghnad Saha, J.C. Ghosh, Raman, Bose was content to remain a quintessential scientist. He never built his own institute. The S.N. Bose Institute, which was built, came up after his death. Indeed, he was nominated as a member of the Rajya Sabha and he did accept it in 1954 and he remained a member for 5 years. But he spoke only rarely and just 3 speeches survive, one opposing preventive detention, one on solving the refugee problem and one on the role of the new UGC. These are still burning questions today or the equivalent. He retired from the Calcutta University at the age of 62 in 1956. Now, before he had retired, in the last 2 years before he retired, suddenly Bose became very active and started writing papers on Einstein's unified field theory. So, this unitary here doesn't mean unitary in the modern sense, it means unified. So, one paper after the other came in this period, 1952, 53, 53, okay, January 54, 5 papers in quick succession. And these papers he sent to Einstein, and this time things were different. So, Einstein was very old at this time, by this time. So, but this time Einstein invited Bose to come and work with him in Princeton. Okay. Of course, by this time nobody else wanted to work with Einstein. So things were different. However, the trouble was that before that Bose had gone to Russia. So these were the McCarthy days. So his visa was refused. Again, familiar story. And then after a year, when he reapplied, they did give him the visa. But when all was, at this time he had money to go. He got money also to go for all this. But then Einstein passed away. So he couldn't, this long cherished dream of actually collaborating with Einstein never happened. But I found it's interesting that in a stamp issued on Bose in 1994, what is mentioned is not the Bose statistics, but the torsion, which is the cornerstone of Einstein's unified field theory of gravity. So, I don't know who was consulted for this, but anyway, perhaps that's how Bose would have liked it. He was appointed Vice Chancellor of Vishwabharati, the university set up by Rabindranath Tagore at Shantiniketan, but he did last more than 2 years. So, that's also not unknown, but apparently Bose complained that whatever changes he wanted to make at Vishwabharati, people raised their hands and said, no, this is not how Gurudev would have liked it. So, after 2 years, he simply resigned and came back. So, he was elected a Fellow of the Royal Society as late as 1958, and that is he was nominated by Dirac, and Dirac had come in 1957. He was aghast to know that the great S.N. Bose was not an FRS, so he remained a good friend, so Dirac nominated him. He was appointed National Professor for 5 years in 1959, and they kept repeating it, renewing it till so long as he lived. Calcutta University made him Emeritus Professor in 1959, gave him a lab and grants to work, but he was now 65. He continued to train students in experimental techniques. His real love actually was for the laboratory. The Bangya Vigyan Parishad had been formed with Bose as president in 1948. He continued to advocate the teaching of science to his mother tongue. He was appointed president of the Indian Statistical Institute at age 73. He would remain the president till his death. So a few pictures. This is Bose with Paul Dirac. And there is a story that apparently when Dirac visited Calcutta, so Dirac was sitting in the back seat of an old ambassador car alone. And Bose already had a student sitting in the front. So there was a driver and there was a student sitting there. So Bose decided to squeeze in with the student in front. So Dirac said, Professor Bose, there's plenty of space in the back. Why didn't you come at the back? So he said, you see, I believe in Bose statistics. So that's a good story about him. Then we see him here leading the procession because he was president of ISI. This is with academician Kolmogorov. And then with a young Indian scientist. Anyone can recognize him? Yes. That, of course, is Jayant Narlikar. So, and as you see, Bose is very old at this stage. So one more story of this time. So Bose used to work in the Science College, and one day it was the day of the election, and people found that Bose was very actively asking people, have you voted? So they would say yes. So then he would, from his pocket, he would pull out a small bottle and a piece of cotton wool and say, okay, see, now I've removed your election ink mark. Now you can go and vote again. So this happened for quite a few people. I don't know if they voted again. But after some time, the news reached the local police station. So the policeman found himself in a bed. Okay, he could not arrest the national professor, but he couldn't allow it to happen also. So he actually came in person and said, Saab, aisa mat kijiye. So that's a well-known story. All right. Now, in 1974, it was Bose's 80th year as well as the 50th year of the Bose statistics. So there was year-long celebrations were held in Kolkata and elsewhere, a long round of seminars, symposia, felicitations, cultural programs. And the most enthusiastic participant in this was Bose himself. And he was very happy. And in fact, he felt vindicated. He said, now I feel I do not need to live any longer. So he was completely satisfied. So I have this little clip of Bose at one of those functions. So walking with a stick at those days. Unfortunately, the excessive strain told on this man's health, the old man. 1 month after his 80th birthday, he passed away quietly at his Kolkata home. And not since the death of Tagore was there such an outpouring of public grief. So the funeral cortege was accompanied by a host of people. I have only this very grainy films division picture to show you, but apparently it stretched for more than a kilometer. And so Bose's body was confined to the flames, but the flame he lit of Bose statistics certainly lives on and will live on as long as. So finally, one has to understand Bose because a lot of things have been said about him. A lot of fiction has gone around about him, some about his great mathematical abilities, some about other things. But let's try to first understand that he was really a complete product of the Bengal Renaissance. He was a mathematician, physicist, chemist, spectroscopist, and so full of the milk of human kindliness. So that people have always pointed out. He was a very kind and very gentle person, and people who would go to him for any kind of help would always find him forthcoming. Very rarely did he send anyone back, okay? Though there are notable examples of that. The work he did in 1923 and 24, it bridges the gap between the old quantum theory and quantum mechanics. So in the words of Shakespeare, we could say he could see quantum mechanics as through a glass darkly. So he had amazing intuitions as to what the right thing would be, but he didn't know the reasons people would give it for it later. But he just used the right results. Nobody knows how he came to those results. I think he himself didn't know how he came to those results. But when quantum mechanics actually came, clearly he didn't like it. It's not that he didn't understand it because he was doing quantum mechanics later. But clearly he didn't like it. He didn't also like the problems, otherwise he could certainly have done it. And it is important because people have later claimed that his great work was achieved by serendipity. No, it was not achieved by serendipity, but by deep reflection. He had been thinking about these ideas for a couple of years, and the basic assumptions he made were physics assumptions, good physics assumptions, not just some mathematics, which, as I showed you, that mathematics could be pulled out of a textbook. So Ashok Bose, one of his students, not a relation, he wrote, I happened to see a Dutch paper which gave me the idea that our work was worth publishing. I suggested it to him, he would not listen. Paper? What do you want a paper for? Have you understood it? Fine, now you can throw it away. So it was like a game. He was intense, but as soon as he saw the solution, he had no use for it. He threw it away. But he had a child's curiosity. If he was interested in something, he would go 500 miles knowing there would be no use for it. He did not mind wasting time. But Ashok Bose did mind wasting time. So he went on to do his PhD with Heisenberg. Anyway, talking about his mentors, he says one should not expect people like him, Bose, to be doing routine work in one particular line. That would be insulting him. They means he and Heisenberg are after the final truth, not caring for what can be achieved on the way. Everything is eternal. He was not interested in small matters, wanted to go to the depths. He was an aristocrat. So it is an aristocrat of science that I think we should remember him. So here is my last slide. Bose accepting, just being served the food at Shantiniketan. I believe he was the Vice Chancellor. And so let us thank Bose for all he did for us, and I thank you for your patience in listening to this very long talk.
So, about I think 14 months back exactly, talk about history of particle physics in India, and now we have this talk. And I think if you want to hear one talk that is on S.N. Bose's life and physics, I think that is the talk, and the fantastic trademark Sreerup's talk again. Since we are quite late, so we don't have any question answer, but I request people to kind of interact over a cup of tea, but not before giving this little.
Okay. Thank you. Thank you. Very nice picture.
Thank you very much.
Okay.
Thank you very much.
Thank you.